Now that we've talked about nucleophilic substitution in general, let's focus on the SN2 reaction. If we have a methyl halide and we react it with a good nucleophile such as hydroxide, this will go through nucleophilic substitution to give methanol plus Br minus. Now, in the previous chapter, we looked at how to convert alcohols to alkyl halides. Now we can see that we can convert alkyl halides to alcohols. For this reaction, the rate law says that the rate is equal to a rate constant K times the concentration of methyl bromide times the concentration of hydroxide. So this is an SN2 reaction, substitution, nucleophilic, bimolecular. If we think about the details of the reaction, let's say we have our substrate like this, and then our nucleophile can add. Now, the nucleophile is going to add to the back side, the side opposite where the leaving group is. This is a concerted reaction, and so the bond forming and the bond breaking are happening at the same time. If we think about the transition state, our oxygen-carbon bond is forming, our carbon-bromine bond is breaking, and these hydrogens flip inside out. So in the transition state, these guys are going to be kind of planar, and then as this bond continues to break and this bond continues to form, this continues to turn inside out so that at the end we have our groups inverted. For this particular example, it doesn't matter because we don't have a chirality center, but it's important to think about how this flips inside out like an umbrella caught in the wind. Forgot to add some detail to my transition state. Our hydroxide starts out with a full negative, and in the transition state, it will have a partial negative. Our bromine ends up with a negative. In the transition state, it will also have a partial negative. So the nucleophile attacks the face of the carbon that is opposite the leaving group, which causes the molecule to flip inside out, which leads to overall inversion of configuration, or just inversion of the 3D arrangement of the groups. In terms of an energy diagram, if this is the energy of our starting materials, then this might be the energy of our products, and we're going to have the reaction progress look something like this. Here is the activation energy. Remember, we are going from our starting material to our transition state. The transition state is going to look something like this, where bond breaking and bond forming are both happening at the same time. Not necessarily to the same extent, but they're both happening at the same time. This is a single step. Remember, we talked about elementary steps, and an overall reaction can consist of a single elementary step or multiple elementary steps. This one is a single elementary step. It is substitution nucleophilic, substitution because that's the overall change, nucleophilic because hydroxide is acting as the nucleophile, bimolecular because two molecules appear in the transition state of the rate determining step. There's only one step, so it has to be the rate determining step. So when we have a reaction where the bond forming and the bond breaking are happening at the same time, we call this a concerted reaction. So here we have the general information then for an SN2 substitution. When we first saw SN1 and SN2 reactions, we were talking about the reaction of an alcohol with HX to form Rx plus water. And here, if we have a tertiary or secondary alcohol, they will undergo SN1. If we have a primary or a methyl, they will undergo SN2. But with other types of nucleophilic substitution reactions, spoiler alert, tertiary will still proceed by SN1, primary and methyl will still proceed by SN2, but secondary can undergo either SN1 or SN2 depending on the nucleophile that's used. We'll talk more about that later, but for now, I want you to trust me that this particular reaction can proceed through an SN2 mechanism. So we have a secondary bromide, and this carbon is a chirality center. And right now, what we are looking at, bromine has priority 1, the ethyl group 2, the methyl group 3, the hydrogen 4. So we're going 1, 2, 3 counterclockwise. So this has the S configuration. When we add sodium cyanide, the cyanide, remember this is our nucleophile, the cyanide is going to add to the back face, pushing away the bromine leaving group. Let's think about the transition state. So the nitrile carbon will be forming a bond with the carbon that was connected to the bromine. The carbon-bromine bond will be breaking. And while this bond is forming, these groups are going to be pushed, instead of being on the left side, they're going to be pushed toward the center, so that we're going to have something like this. Here's our methyl, here is our hydrogen back behind, and then here is our ethyl group in front. This will have a partial minus, and the bromine will have a partial minus. Now this will continue so that these groups will continue to move to the right side as this bond is broken and as this bond forms completely. So here we end up with our carbon connected to our carbon, and here is our methyl group, hydrogen and ethyl group, plus Br minus. Now, if we look at priorities, we have carbon, carbon, carbon. This carbon is connected to nitrogen, so this group has priority over this group, which has priority over this group. So now we are looking at 1, 2, 3, and our hydrogen is 4. We are going 1, 2, 3 clockwise, and so this compound has the R configuration. So just looking at the structures, we can see that they have opposite relative configuration. And also when we assign our S configuration, we see that they also have opposite absolute configuration. So SN2 reactions occur with inversion of configuration. So inversion of configuration, this is an important consequence of this concerted reaction. Because the bond forming and bond breaking are happening at the same time, the nucleophile has to approach from the back side of the carbon opposite the bromine, and then that's what leads to the inversion of configuration. So by understanding the mechanism, you can understand and predict the stereochemistry.